So we've actually come to the point in the course where we need to talk about leftovers. And honestly, leftovers is not really our concern. It's the thing that runs out first. So I don't know what that's called in food, but it's worthwhile to talk about food because A, we can relate to it, B, I haven't had lunch yet. But if we start thinking about maybe a cheese sandwich, we'll go with a really simple cheese sandwich. The recipe, you don't have to write down the recipe for a sandwich, I hope, but the recipe for a simple cheese sandwich is 2 pieces of bread, 1 piece of cheese. Now, if I were to rummage through the cupboards and I were to find 20 pieces of bread and asked you how many sandwiches could we make, hopefully you'd say there I could make 10. If I said, well, what if I only had 15 pieces of cheese? Well, with 1 piece of cheese making 1 sandwich, I could make 15 sandwiches. But the what if question that's important is what if I had both at the same time? Now, obviously, I'm not going to start skimping out on the bread or the cheese or cut pieces of cheese in half or cut bread and whatever or throw it away. But the bottom line is I could actually only make the 10 sandwiches and I would have leftover cheese. So there's my leftovers, but what's interesting or what's important in terms of the chemistry is not the cheese being left over, but the bread running out first. And that's what we're going to be focusing on when we get to start talking about reactions. So let's talk about a reaction, and I picked a reaction that has kind of a similar idea as a sandwich, but you certainly wouldn't want to eat that stuff. If I had 2 moles of potassium here, well, the same rules are going to be followed as with the sandwich. 2 potassiums make 1 potassium sulfide, so if I had 2, I could make 1. All right, fine. What if I had 1.5 moles of sulfur? Well, 1 sulfur makes 1 potassium sulfide, so I could make a total of 1 potassium sulfide. Well, what if I had both at the same time? Well, now that's a little bit different from food, but really not different from food. I'm still not going to eat it, but the rules would be the same. I'm going to run out of potassium first because the potassium I have available is only able to make 1. So instead of talking about sandwiches now, I'm going to talk about chemistry and say that the amount of product is limited by, in this case, the potassium, the reactant that runs out first. And the reactant that runs out first is now called the limiting reagent. So if I have a reaction and I give you this question, now in this case the reaction is fairly simple. It's 1 mole reacts with 1 mole to make 1 mole. But I could look at that and say, well, I've got a smaller amount of sodium hydroxide than I have a hydrogen chloride, or if we haven't done the nomenclature, HCl, I've got 3.5 moles of it and 2.5 moles of NaOH. So if I were to put them together, I could only produce 2.5 moles of sodium chloride because one of just the mole ratios, I'm not going to talk my way through it because I think it's fairly simple and straightforward. All right, so that as an idea, hopefully, is simple, straightforward. That's what we're counting on. But let's step it up a notch. Now in this reaction, obviously the balancing coefficients are not 1 and 1, they're 1 and 3. So if I had 5.3 and 15.5, we need to be careful because to start out and say, well, 5.3 is really small. Well, it's supposed to be a lot smaller because look at the ratios. I'm supposed to have 3 times more carbon monoxide than I have iron 3 oxide. So how do I know if it's the right amounts? What we're going to do to figure out the limiting reagent is we're always going to start with numbers of moles. Even if we don't have numbers of moles, we'll have to get numbers of moles first. And then what we're going to do is we're going to divide each thing by the balancing coefficient. Now what that's going to do is it's going to, let's say, remove the influence of the balancing coefficient, reduce everything back to 1-to-1 kind of thing. So if I were to take that reaction that I was just talking about and I had 5.3 moles, well, I'm not going to really divide by 1, but I'm going to divide by 1. 15.5 divided by 3. So now I remove the fact that I'm supposed to have more of the carbon monoxide, and I end up with 5.3, no big surprise, hopefully I didn't spring that one on you, and 5.17. Well now, even though 15.5 is a larger number of moles, it's not quite large enough, and it is now limiting reagent because I don't have as much as what I'm supposed to have for 5.3 moles of iron 3 oxide. So at this point, once I've divided by the balancing coefficients, now I know which one's the limiting reagent. It's now the smaller one. So not the smaller one that I started with, but the smaller one that I finished with. Well, I'm not done the question yet. I've done all that work, but all I know now is which one is limiting. Now I have to answer the question. Don't forget to do that. My question was how much iron would be produced, Fe. Okay, well, I don't have to worry about the iron 3 oxide because I had more of that than I needed. Right? I didn't have to worry about how much cheese I had because the bread ran out first. Well, carbon monoxide is limiting. I run out of it first. So it's going to determine how much product I can make. So now I'm looking at 3 moles of carbon monoxide producing 2 moles of iron, or whatever ratio I actually have following that original recipe. So now this is looking like the second step of stoichiometry, because it is the second step of stoichiometry, looking at how many moles of product can I produce from that many moles of reactant. And I end up with 10.3. Okay, we're going to take it a step higher. And what we're going to do is we're going to take a reasonable looking reaction, and we're going to run it through a full limiting reagent question, because we never work with numbers of moles. Not initially. We always start with masses. So now what? Well, this kind of looks like a stoichiometry, but a bit different, because now I have 2 masses. I'm asked for a final mass. I still have that mass of unknown, but I have 2 known masses. Here's the thing. Only one of them is important. The other one is limiting. Well, which one? We don't know yet. So our first job is going to be turn those into numbers of moles. And really, that's going to be the first job almost every single time you see a measured amount, whether it's a mass of a solid or a volume of solution or anything else like that. Figure out numbers of moles. Almost always we're going to work with that first. Then we're going to determine the limiting reagent. Same thing that we just did. Take those numbers of moles and divide them by the balancing coefficients. And then we're going to do stoichiometry to find the answer, only looking at the limiting reagent. So each one of those steps is fairly simple, straightforward. We've done it, okay, the one we've only done once. But we've done stoichiometry a bunch of times, and we've calculated numbers of moles a bunch of times. And this one in the middle is actually pretty easy. All we have to do, actually it's down here, isn't it? All we have to do is divide by the balancing coefficients. All right, so where do we start? We start with calculating numbers of moles. So we take our masses and we divide them by the molar masses. Too easy. And we get a number of moles of one, we get a number of moles of the other. And please pause it and do the calculation too. If you haven't pushed the buttons on the calculator, then none of this means anything to you. Then we divide those numbers of moles by the balancing coefficients from the reactant side, keeping in mind which one is which, because that's usually where we make our mistakes. All right, so we take our number of moles of aluminum chloride and we divide that by 2. We take our numbers of moles of magnesium oxide and we divide that by 3. So we get a number that where the numbers of moles, the balancing coefficients have kind of been removed. Now I know which one is limiting, the smaller one. So now I can completely ignore the magnesium oxide and just work with aluminum chloride. So now the question becomes, how much product can I make with that amount of aluminum chloride? Now what's kind of important to remember is that previous number, let me just go back to it, 0.059, is not something we're going to use, because we divided it by the coefficient. So now that number is just sort of, I want to use the word reduced, and I don't want to use the reduced form of it. So going back to the reaction then, that is my limiting reagent. So that's the only one that matters. It runs out first, it runs the show. So now I do a full out stoichiometry. Now, you might be thinking, well, hey, I already did step number 1. I already took the mass and turned it into numbers of moles, which is true. So you don't have to redo it. It's just that for most people, this is going to be the familiar form of stoichiometry. So it doesn't have to be that you go right back to the beginning, but this is what we're going to be familiar with. And then you find out 6.04 grams of aluminum oxide. There we go. So we did all 3 steps. I'm going to leave you with one to try. And it's really important for you to try, and of course we're going to be doing some examples in class, but it's going to be one of these things that because we know all the steps, you're not going to have a lot of practice because most of it's doing stoichiometry. So anyhow, let's try this one. So you're going to give a reaction there with ammonia and oxygen reacting, and the question is with 53 grams of ammonia and 185 grams of oxygen. Find the number of moles of each. Divide each by the balancing coefficient, and then do stoichiometry just with the limiting reagent. And when you have that, you will be feeling like Albert Einstein, because it's a lot of work. I get that. But we'll talk about the kinds of questions you can expect to see. We'll talk about the kinds of questions that you will, how we'll change it so that we're testing what's important. Anyway, we'll talk to you in class.